All right. Thank you. Sorry.
Mine, but here,
Yeah, no, what's the least painful way to, I think I have to hide the other thing first, right? There we go. Sorry, I'm not a Zoom native. Um, all right. So, yes, I'm here to talk about the ASTA system and project at the Allen Institute for AI. Um, So I'll start with an idealized picture of what the scientific workflow looks like. So scientists start by searching for and discovering previous work. They'll read and understand a handful of those works, and that allows them to generate hypotheses. Then they can design and execute experiments to test those hypotheses, analyze the data that comes back, and finally write and promote their work. Of course, this is an idealization. There's, a lot of backtracking and a lot of different styles across different scientists. The ASTA project is aimed at building a scientific assistant that assists with all of this workflow. And we don't want this to be just a scientist that chats with you. We wanted to use all of your data and tools. So your experimental data that you get back, the scientific literature, code you write, Asta should be able to read and write and use those tools just as you do. So this is the vision. I wouldn't say we've accomplished this yet, but we released a handful of tools as steps toward this vision. And I'll talk a little bit about each of these. So this is our releases over the last 12 months. One exciting thing from these releases is we've gotten a bunch of data. So we have more than 200,000 user interactions. And I'll talk a little bit later about how we're using some of this data to build evaluation benchmarks to help the field improve agents like these. All right, so let me first just give you a concrete look at what some of our tools can do. So there's the Asta Find Papers tool that I'll show you first. This is a search engine for papers, but it's designed to find the hard to find papers. So you can search for things like, oh, what was that paper where they were showing method Y outperforming method X? And it will dig up papers that meet that criteria. So here's an example, searching for non-summarization papers by Marilla Lapata. This is somebody who writes a lot of summarization papers, but we want the ones other than that. And this is hard to do with a conventional search engine, but it works well with Asta Find Papers. So the system decomposes and formats your query, and after a while returns this list. And this is, in fact, a bunch of non-summarization papers by this person. You can then go over to this right-hand channel and ask for, give me just the somewhat relevant ones. And those are the ones that match the Marilla Lapata part of the query, but not the summarization ones. So now these are actually summarization papers. So this is the Find Papers tool. That was a little bit of a quick run through, but hopefully gives you the flavor. The next tool I wanted to talk about was the Summarize Literature tool. So this is a tool that summarizes and produces long form reports. So instead of a list of papers, it will actually it will produce a long form report that summarizes the papers. It's a little bit similar to like OpenAI Deep Research for folks who have seen that tool. And I'll talk a little bit later about ways in which this tool outperforms some of the existing tools. But first, let me show it to you on a query. So we could ask this question, what's the Venn Ebers technique, this particular mathematical technique? This tool, again, analyzes your query, sends it off to some indices that I'll say a little bit more about in a second. This process takes a while, it takes a couple of minutes. I'll jump to the conclusion. When the report's done, it's broken into these sections, identifying key themes of the answer. You can dig into these themes. Every claim that the answer makes is supported by citations. When you click on those citations, you learn about the paper and its authors, and you get excerpts from the paper that support the citations, and then you can go and actually see those within the context of the paper. That's the Summarize Literature tool. And the last one I'll show, and this one's not public yet, but we're excited about it, and it's going to be available later. Later, actually, in the month of November, we expect, is called Analyze Data. So this is a tool that helps you interactively analyze your data. And here's how this works. So you can load a data set and describe it to the tool. So this is the user saying this data set captures participant level responses in a behavioral study. that evaluates how humans detect lies. And then you can give the system a question, a hypothesis over this data that you want it to investigate. So the question is, do female participants switch to AI advice less frequently than male ones in the AI accuracy treatment of this data set? Okay. So now this tool will open your data, write code to analyze it, and ultimately produce this contingency table, and then come to a conclusion, which in this case says that yes, this indicates that there is a significant difference in AI switching behavior in this data set. And then yeah, you can ask something like, can you plot this for me? And it'll produce a plot that summarizes it. All right, so that's kind of a whirlwind tour of 3 of the tools that we have. And that went by quickly. Fortunately, these tools, except for the last one, which is coming shortly, these tools are all public and they're all free. So I encourage you to go to this URL, try the tools, and see if you like them, give us feedback on your queries. And this is at asta.allenai.org. All right. So that's a brief overview of the Asta system. You might be wondering, like, gee, there are other tools that do things similar to the ones that we just showed. So how do we know, do these tools that I just showed offer advantages over those other ones? Or, how can we tell that any of these tools are actually like really good and reliable? That evaluation challenge is what led us to develop AstaBench, which I'll talk about relatively briefly. In a longer talk, I'd kind of go into a lot of details on this, but for today, I'll keep it kind of brief. And then I want to dig in a little bit into how we built some of these tools and some of the user experiences we're seeing. So I'll talk in more detail about the summarized literature tool, and then a piece of AstaBench that evaluates that tool called Scholar QA CS2, where CS stands for computer science. This is a benchmark that evaluates Asta's performance on computer science questions. Along the way, so there's like a ton of open questions here and work still to be done. And so I'm also going to outline 4 open challenges in the area of AI for science. All right, so let me jump right into talking about AstaBench. This is work led by Jonathan Bragg at the Allen Institute for AI. All right, one question that comes to mind is, there are already a lot of benchmarks for evaluating AI systems. Why do we need another one? We found there were actually 5 criteria that were missing from existing benchmarks that we wanted to build into AstaBench. So one is we need benchmarks that represent real world usage, right? So we built these real tools for people to use. And we want evaluations that are grounded in those kinds of experiences that people use in the form of products they're using all the time. We also need the tools that those agents can harness to be real world things. And in our case, we have a literature index, which is the real one that we use both on Semantic Scholar and on those Asta tools. And that's part of the benchmark. And so anybody can get an API key to use that tool, and they get to operate in that sort of realistic environment. It's also really important to control for confounders. So it's a reality of these kinds of agents that often they can just spend more compute at test time and do better on tasks. So even simple things like you run the same agent multiple times and take a majority vote of the outputs, those things reliably improve performance. And so if you don't account for the compute cost, then you can actually end up saying that an inferior method actually appears better than a truly superior one. People are excited about general agents that can handle any task. We need benchmarks that are appropriate for those agents. I won't say too much more about that. And then also, right, when you release a benchmark like this, you need to release a bunch of reference agent designs, which we also did. I won't belabor this table, but this is like a list of the other benchmarks that people have built, and the columns are like the reasons why they don't have the characteristics I just called out, but our benchmark does. Okay, so very high level results. Here's what we're seeing from a set of different agents. And again, so the y-axis is like measure of performance. How good is the system? The x-axis is cost, getting more expensive as you move to the right. Our current Asta system is the best performing, but also like the most costly. So that, there is this trade-off. There's this Pareto curve, right, at the top of this graph of agents that achieve the best performance per unit cost. So I won't say a ton about this, although I will call out that even our best system, right, is just a shade above 0.5 performance on this benchmark. So it's really not not super great.
Actually,
Yes, go ahead.
question on that last spot, it's so hard to read all the individual things, that dashed line and the other points that it connects, what are those other points? Are those previous versions of Asta, or?
Yeah, no, it's a great question. These are other generic agents that can perform across all of the Asta tasks, and they're using the same tools as Asta, but just in different ways. So they don't, yes, it is a great question. The Asta includes a bunch of hand-designed workflows, and I'll talk about the one for summarized literature that are aimed at these particular tasks. Those workflows tend to be a little bit expensive, but they also tend to perform better. Every other point in this graph is a generic agent that just gets a description of the task and tries to do its best to carry it out. And it can sort of spend more or less in doing that. There's also a bunch of different foundation models in here. So GPT-5, GPT-5 Mini, O3 is in here, and Gemini 2.5 Flash. So you don't actually need to see all the details, but I mean, they're available in the blog post and stuff in the paper if you want to see them. But that's what's going on here. So there's a whole bunch of different generic agents. There's two different generic agents. One is a React agent, and the other one's small agents. And there's a bunch of different base models. All right. These are the tasks that go into the AstaBench benchmark. I won't go into these in too much detail, but they're in these 4 categories. So we've got literature understanding. We've got agents that try to write code and execute it, data analysis, and then also end-to-end discovery. So these are the 4 sort of categories of benchmark. Many of them are taken from previous work. A few were new in the AstaBench data set. In a longer talk, I'd go into some detail about how we designed those tasks, but for today, I'll just summarize a handful of high-level points. So the first one is the overall performance is not good. Across any of these categories, it's like none of these agents are actually that good. So you hear a lot of headlines about, scientific research being automated. What we find on our benchmark is like there's huge room for improvement. The reason you only saw generic agents in that graph a moment ago is because commercial tools like OpenAI Deep Research, which I'll come back to in a second, can't do all the tasks, right? So OpenAI Deep Research doesn't write and execute code for you out of the box. And so that's why we only compare it against generic agents there. We did see that the Asta, special purpose workflows were better than the general purpose agents, although it came at some cost. This was an interesting finding. So this fourth one, it turns out that actually sometimes you can use a more expensive language model and actually reduce the cost. And that's because the amount of work to do by the agent is a free variable, right? So the agent can decide, how many queries it wants to do, how much thinking it wants to do, and lower cost models can make better decisions of that type, right? Worse decisions of that type, making them ultimately more expensive. And then, there was this detail about GPT-5, which raised the performance of the generic agents, but actually when we plugged it into our Asta pipelines, it often lowered performance. Just briefly, all this stuff is public. Please, use it. And things like, the search index, it's really hard to stand up one of those things. You can use ours, just for free. So if you want to experiment with scientific agents, we really encourage you to use this stuff. All right. So that was AstaBench in brief. Now let me dig in a little bit to the summarized literature system. So I think you understand how this works. You ask a complex scientific question, you get out a report. These 3 people were the leads of this work, but there are others involved. So for this audience may not care quite as much about what's going on under the hood, but just really briefly, we get a query and we submit that query to 2 different indices. One is this sparse and dense thing that uses learned embeddings, and the other, and that has 12 million full text papers. Then we also use the Semantic Scholar API, which has 108 million abstracts. And this is the raw material we're searching. And then we re-rank those to select the good ones, and then it starts getting expensive because we send this to LLMs. So we ask LLMs to say, what are the most informative snippets that you got out of the index, and what exact quotes of those are most relevant to the question? Then we organize those into those themes, which you saw, right? Those are the expandable sections in the answer, and then we write the response one theme at a time. So this isn't like a radically novel architecture, but is one that we found to work well and that we tuned in various ways. All right, so a handful of statistics about how people are using this. So this is the traffic that we're getting, it's kind of went up and has held steady. One exciting thing about this graph is that the returning users make up a substantial fraction. So monthly active users use the tool at least twice. Returning monthly active users use the tool on 2 distinct days. And so we're seeing that 60% of the monthly users are actually returning ones, which suggests people are coming back to the tool, like it's actually helping them do work. We collect feedback in the tool and get thumbs up and thumbs down. Most of that's positive. Yeah, I think you kind of have to take that with a grain of salt because it's only like certain people that click those thumbs. This is a simple, but I think kind of fun graph. So this says which sections of the answer do people expand? And, they do tend to expand the later ones less often, although interestingly, they don't expand the first one as much. And that's because the first one is always a background section. So, only some users want that. So a decent chunk of users are skipping it. Here's just a little bit about the kinds of questions people ask. So depending on their experience level, the most experienced users tend not to ask these broad questions like, what is deep learning? They ask less of those and more, asking for specific concept definitions or causal and relational things. So we're still digging into this data and hope to do a lot more. This is kind of a little bit about the amount of data we've gotten so far, and we're going to package this up and release it. We hope in the next month or two. These are people who explicitly opted in to having their data be shared. One thing we have released is a set of citations. So, the field of AI is generally doing a poor job of giving credit to or poor is a little strong, but the field of AI could be doing a better job of giving credit to the people whose content gives rise to the amazing feats of large language models. When you're in a retrieval augmented generation system like we are with Asta summarized literature, you can do better because you know about which papers you're explicitly citing. In general, crediting source material in a large language model is like a fiendishly difficult problem. But when you're explicitly citing things, you can record those and then report them to people. And so that's what we did with this data set. We released, about 5 million citations that have powered our reports. The goal is to kind of give credit to the authors who did that work. And then also provide a data set about how systems are citing science right now. So these are our top 5 papers. For those of you who, read computer science papers, these are usual suspects. And this I thought was an interesting analysis. So a concern with AI tools is that they're going to focus more attention on the most cited and most popular work and end up crowding out other less prominent work that is still important. What we're seeing so far in the statistics of what we're returning is the opposite. So actually, when you compare how often Asta cites the most prominent work in its reports, it actually cites the most prominent stuff less often than human authors do when they write papers. So that's what we're comparing here. So and so at the 90th percentile, 63 of the citations in papers go to the top 10% of cited papers, and only 34% for Asta. And then it gets more extreme as you go up this list. So we weren't expecting this, by the way, but it turned out to be true in our data. Okay, so that was Asta summarized literature. I'm going to just very briefly talk about this Scholar QA-CS system or Scholar QA-CS data set, and then cover some open challenges and plan to conclude. So how do we evaluate how good our summarized literature system is? Well, we have these four metrics. What does the answer cover all the important stuff? Is everything in the answer relevant? And then 2 measures about citations. So are all the claims supported by citations? And for every citation, does it support at least in part some associated claim? So those are 4 measures. We're using a language model as judge to evaluate each one of these. In the case of answer coverage, we're doing a little bit more work. So we actually go and so it's hard to say what ingredients should be in the answer. The way we define that is by querying a whole bunch of systems and taking the union and trying to pick the best stuff. So we query a bunch of these state-of-the-art commercial systems and open ones as well. And we get the reports, we use a language model to extract their key points, and then we use a language model again to cluster and select those. And then we're left with must-have and nice-to-have ingredients. And then this is a rubric by which we evaluate all the future reports. And we're going to use a language model as judge to do that evaluation. For relevance, we just use a language model as judge to classify different sections as good or bad. Most of the time they're good, but sometimes they're bad. And then for these citations, again, we use the language model as judge, and we in particular use those excerpts, so which kind of went by quickly, but our system and a lot of the other systems give you an excerpt from the cited paper that's supposed to support this like claim that's associated with the citation. And we're using that as a key ingredient to evaluate, does the cited paper actually support what the system is saying? Okay, so and here are the headline results of this comparison. And now you'll see we are actually evaluating against a bunch of the commercial systems. The Asta system performs the best, and this was a little bit of a surprise to us. But it's important to note how it's performing the best, right? So it only wins in the citation measures. And some of the other tools, especially these like Perplexity and OpenAI Deep Research are very popular commercial tools. They do very well in the first two columns, but really less well in these latter two columns. And I think, the top three systems are science specific. And so what you may be seeing here is that our evaluation and our system are designed for a scientific audience, and likewise, so are these other two systems near the top. And one of the values we build into the system and the evaluation is that what we say should be directly supported by the literature that we're citing. So it's actually like not enough for the what we're saying to just be factual. It actually needs to be correctly supported by the citations. So our evaluation emphasizes that. And I won't go into these examples, but in the next two slides are just sort of a couple of concrete examples of OpenAI Deep Research saying things that may be true but are not supported by their cited documents or are partially supported. So this is a particularly illustrative case where there's a statement here about multiple systems and multiple learning techniques. And the citation only covers one of those systems and one of those learning techniques. So it's like covers part of the claim, but not all of it. And that's something we mark as wrong. Okay, this, if I had a little bit more time, I'd kind of go into this more detail, but I'll for right now, just issue a caveat, which is the level of agreement. If you ask a person to look at two reports side by side and say which one's better, and then also compare those two reports using our eval with those four measures that we painstakingly developed, the amount of correlation between those two judgments is actually not super duper high. And that's what this slide is saying. So there's still a lot of work to be done to produce a good evaluation. And in fact, I would go further. So we have these four measures that we kind of like. But importantly, they don't really evaluate what, for lack of a better term, I would call scientific understanding. So here's an example of a query. Has anyone scaled topic models to hundreds of thousands of topics? So topic modeling is a particular NLP technique. Does it improve held out likelihood? And what this answer is saying, well, there's a conflict. So some work says, yes, there's clear benefits. Other studies say, no, there's not clear benefits. But here's the thing, if you actually dig into these details, this isn't really a conflict. What's going on is that earlier methods, everything down here that doesn't show gains is from 2010 and earlier and uses earlier methods in small corpora. These things at the top are from 2015 and later, and were specifically designed to handle large numbers of topics, very different methods, and they use large data sets. And that's why they're showing different results. This is from the Asta system, and it just doesn't tell the story at all, right? And so a lot of times things that appear to be conflicts in science are actually require this more nuanced understanding of exactly how the methods and experiments work. And tools don't do that today, and our evaluation also doesn't touch that. Okay, so open challenge number one, how do we actually evaluate these things reliably? And I'll just quickly run through the remaining challenges, but I did want to take two or 3 minutes for this little detour. So you might wonder, LLMs, they can do amazing reasoning. It's like you hear about this all the time. Why Do we see shortcomings like the one we just saw? And that was, a frontier language model generating that stuff. So I'm going to illustrate a part of why with an example from chess. How many people would say they know like the rules of chess? You don't have to like be a grandmaster, but okay, most people know the rules. Okay, good. I mean, if you don't, you may still get something out of this example. It'll go by quickly. So imagine giving, if like a person or a language model just this text. So you don't have a chessboard in front of you, but you just get this text, and you're asked this question: what's the best next move for white? This is really hard. So, I play chess as a hobby, and I couldn't answer this question. Like, I can't track the game state for 8 moves for each side, which is what this means. So this is the board position, and there is a right move. What's interesting is you give a language model just this text, and it completely nails this question. It gets it exactly right. So not only does it pick the right move, but it tells you why, white's at a big advantage in this position. So this is very impressive. This is like superhuman performance for like most humans who play chess. But let's talk about this other question. Now I'm playing chess, but with a new rule: pawns can capture by jumping forward 5 squares. So a white pawn on a2 could capture a black piece on a7, even if there are pieces in between. What's a good first move for white under these new rules? Does anybody see it? If I gave you enough time. Take the queen's pawn it's not a bad move. It puts the king in check, but the king has to move out. It may be winning. Yeah, that was okay. So right, there's also you can take f7. But the best move is this one. So this is mate in 1 because the king has nowhere to go, and right, it's so this is checkmate. And so if I gave you enough time, you would get this, and you don't even need to see the board in front of you. Like if you play chess, I think you don't even need the board to answer this. So that's I think a much easier question, right? It doesn't require like tracking the game state a whole bunch. So how do LLMs do on this? The answer is terribly. So this was always, for years, for like 2.5 years, this was my favorite question. A new model came out, I would rush and ask it this question. And they were always wrong, with one exception. So O3 Pro did get it right. But then if you ask the question from like Black's perspective, it gets it wrong. So I think it really still doesn't really like understand, but it did get it right once. But all these other models, including GPT-5 Pro, they all failed, despite the fact that this question is way easier than that other one. So what's the difference? The difference is there's tons of data on questions like that previous one. So those moves were not like wildly standard, but they were pretty standard. And there's tons of chess notation and commentary and stuff in the training corpora for these systems. So they've seen all that stuff. They've never ever seen the five move jump pawn thing. By the way, so here's O3 Medium's answer for the 5 move jump pawn. They did guessed capture f7. It's not a bad move, but it's not the best move. I won't go into all of this, but the bottom of the slide is notable. Like the system says this is, quote, generally considered the best first move. So like, people have thought about this, and this is what they decided. Right? It's pretty dangerous for a scientific agent. We don't want it to create an artificial consensus. So the lesson is these systems do really, really well in data-rich settings. And that first chess question was an example of that. But you can create closely analogous settings where humans actually do really, really well. But the systems fall down. And I think this is problematic for science, because science operates in the case where there isn't a whole bunch of commentary about what we're studying already out there in data sets, right? That's kind of the point. And so I think we're going to have to develop new methods. So how to build systems with deep scientific understanding. Very briefly, Abigail Sell and Eric Horvitz wrote this fun paper playing with this co-pilot analogy, talking about how jobs that have a heavy monitoring requirement, but not a lot of direct engagement, lead to high levels of stress, partly why air traffic control is hard. This seems like kind of a bummer from the standpoint of AI agents, because we spend a lot of time monitoring them, right? We look at their output and then make sure it's okay. So what if we flip that around and we let the agents do monitoring for us? So imagine an agent that like is constantly observing the literature, and knows what we've asked about before and can surface to us, oh, here's something you should be paying attention to. Like the answer to your question you asked a couple of weeks ago has changed because of new research. So I think that's an important direction. It's kind of hard to do if accurately at scale. And then how do you communicate just what the user needs to know? So we'd like to turn these assistants into proactive collaborators. The last thing I'll mention is, the very best answer from any of these systems would actually take into account what the user is doing. So how do we do that? How can we use what we know about the user to personalize scientific assistance? And I think there's a huge sort of spectrum. These systems today are useful. They don't return great answers. And in fact, they should return even better than great answers. They should return the best, scientific communication possible for any question we throw at them. Right? So I think that's something we should be aspiring to. And then, right, imagine, how great it will be to have a system that can communicate to us just what we need to know in terms we can understand, that helps us with what we're trying to do. This eventually, that's I think should be the end goal of these systems, and it's something I'm really excited about. Notice there's far less data available to us as we move to the right of this graph. So I think we're going to need new techniques rather than just scaling up. Okay, I know I ran just a bit long, but it's not quite at the hour, so I'll conclude here. Thanks very much.
Yeah, I have a question about the evaluation that you talked about. What test set data set are you using for evaluation, and what is the distribution of that data set in terms of common and uncommon terms, both for author names and for the search keywords?
Yeah, so we for the Summarize Literature benchmark, we're using 100 real user queries. So those are actually queries from our system. We think they're representative of real user needs. In terms of distributions over topics or authors, I don't think we've measured that. So it's a good question. These were randomly drawn queries from the field of computer science. So they're sort of representative in that sense, but I don't have stats on them.
So are these standard? Are there standard data sets for these type of activities that others can?
So there aren't, like, the one we built, we built in large part because there weren't existing data sets for this, or the ones that existed were sort of really lacking. Like we had built the sort of the only pre-existing one, and it wasn't actually as good as we wanted. So in the last month or two, a whole bunch of similar resources have been released. The challenges I called out that I think are, the weaknesses of our benchmark, even this recent one, are ones that I believe are more or less shared by the other benchmarks I've seen. Like there's just still a bunch of hard problems, but there has, caveat to that, there's been an explosion in these kinds of benchmarks. Like there were none or something, or just ours, 7 or 8 months ago, and now there are like 12 of these. So I haven't looked at all of them in great detail, but yeah, good questions. Yes.
Yeah, so sorry, I just went. Okay, so the sort of bottom of the diagram basically says that one of the ambitions for Asta is for it to have hypotheses.
Right.
Okay, so given number 2 that you just got rid of, where it doesn't
Yeah.
have deep scientific understanding, like what does that look like right now, and what do you hope it looks like in the future?
So yeah, great. That is a fantastic question. So I think it still kind of makes sense to generate hypotheses with one of these systems, even though they lack scientific understanding, because the sort of the cost, like very often you can have these systems over generate a lot of hypotheses. Many of them won't make sense, but as long as you put them in front of a human to vet them, you can actually vet them quite quickly. And you're using this hypothesis generator more as a brainstorming tool. Like it could be just surfacing a bunch of random terms or pairs of terms that then you sort of use as a Rorschach kind of test to form your own hypothesis. So like very often these tools can be useful for creative like ideation support, even if what they're saying doesn't actually exhibit or represent a lot of deep understanding. So that's where we are today. I think right in the future, it'd be great to have systems that could actually, that did understand and could estimate the impact of sort of resolving a scientific question in a particular way, and also the cost of doing that. And it could prioritize over, hundreds of thousands of possibilities. These are the ones that, like, given your particular skill set and how expensive and impactful these hypotheses are, these are the ones you should investigate. So we'd like to get to there, but now, currently I would say some of this hypothesis generation stuff is still useful, but it mostly, at least in my experience, is most helpful as something a human scientist vets before it's acted on. Yes.
So, what makes Asta like outperforming the other agents? Is it like, did you like train on some other data like fine tuned, or is it the retrieval augmented generation, or?
So I mean, the summarized literature system is retrieval augmented generation. For right now, like all the systems I talked about today are really just series of prompts that we, honed. Summarized literature, we also like chose embeddings to go in the index and stuff. But for the most part, yeah, these are off-the-shelf tools that we're calling within particular workflows. We are currently, I didn't talk about this, and none of this is in production, but we're training models to hopefully do better on these tasks. Hopefully we'll have a more exciting story to tell about that in a year or so. Yes.
What are your plans for Asta for the experiment plan and execute phase, and how would it differ between computational and lab research?
Yeah, so great question. I mean, right now, where we've used this is with computational research. So where your experiments can be done in software. There's been a lot of focus on just reproducing actually experiments from existing literature. Yeah, as far as what our plans are, I don't know. I can say we would love to work more with our sister institute. So there's the Allen Institute for Biology, brain science and immunology. And we would love to have these tools actually be applicable to their experiments. So that's one direction we're moving in. But I think otherwise, we're likely to stick in software, outside of those other Allen Institute collaborations because experiments are so cheap, and we can understand them because we're computer scientists, right? Which just like counts for a ton. We can tell if the system output is good or bad. Sorry, no, yes.
Yeah, thanks. This is a really interesting talk. I'm wondering if you could just speak a little bit more to the input data of the 12 million artifact, I guess, of scientific work. I'm guessing there's like main differences there. Maybe it's more skewed towards medical literature. So for geoscience, for example, what's actually in there? Are there textbooks, specific journals?
So the 12 million papers, I guess it's not that important to show the slide. The 12 million full text papers that we have, they are all open access, right? Because we need to be able to like freely redistribute the full text. Or freely consume the full text. So we're limited by that. I actually don't know the field of study breakdown of that particular resource. I think it tends not to have a lot of textbooks in it, right? Those are not open access. It's like, things like archive or bioarchive make up a lot of it. I think I can say we do get a large number of social science queries. So this is all the way back at the beginning of the talk, but if you look at this breakdown, so we see like a lot of sociology queries and a lot of psychology queries. So from this, I conclude that these people are getting at least some value out of the tool. There must be, a decent amount of sort of grist for answering their questions. But yeah, I don't actually have the field of study breakdown in that collection. It's a good question.
As a follow-up, maybe, is it possible to have hundreds of papers downloaded from over the years that previously, or maybe still are behind a paywall, but I could see value in like bringing that to Asta? You do that with this summary?
Yeah, fantastic question, and that is something we are planning to work on in 2026. Is a kind of bring your own paper version of Asta. The Allen Institute for AI just released some really good PDF processing models. This almost CR model. So like we're going to use that in conjunction with our indexing, and you'll be able to run Asta on your own document collection. And also your own data sets, right, that are sitting on your desktop. So it doesn't have to be papers, could be CSVs. Great question, and that's something we're working on. Yes.
So on the evaluation I think you mentioned there's a couple of LLMs applied, like extracting ground truth and then LLM as a judge. Is there any kind of human supervision annotation in that process? Or have you studied the kind of noise in that?
Well, so like the one thing I mentioned about the sort of correlation between human pairwise judgments and our eval, that's a place where we've used human judgments. In previous iterations of that evaluation, we actually had humans author the rubrics of what should go in the right answer. We just recently did a comparison that showed those human authored rubrics for answers to questions were actually considered less good. It was in a human annotation study than the ones that were automatically generated by our union of systems and LLM as judge. So that's a case where, you know, it's like one vote in confidence of this sort of actually fairly expensive approach where you have to call 10 systems and, you know, like analyze their outputs versus having humans author the rubrics. I think we need more human in the loop evaluation. We did, by the way, release a system called Arena. This is another thing you can find online where people, you know, folks in the community can just go and rate the outputs of different language models on this summarized literature task. So I encourage you to check that out if you want to kind of understand how hard it is maybe sometimes to assess these answers. You can play around with Arena. Yes.
You, like, how are you approaching the introducing post? As you mentioned, like there is a calculation.
Yeah, so training models is actually, yeah, one of the biggest levers for that. So we think that special purpose models that are trained for these tasks can be much cheaper than, you know, the general models that are sort of powerful for all kinds of tasks in addition to these. So that is probably our biggest near-term lever. There's also things you can do with representing the text. And so this is something we're excited about as well, is like, could we, instead of retrieving all of the paper tokens and putting those in context, could we save just compact like Neuralese representations of those that the system can read? So there's like work like cartridges out of Chris Ray's lab recently that showed you can get like these massive reductions in the size of what you have to store if you learn these representations. So that's another thing. It's like we ought to be able to work maybe not with the text at query time, but instead stuff we've learned about the text in advance. So offline processing. Good question.
Thank you so much, Dan. Any other final thoughts? No? Well, thank you.
Thanks, everyone. Thanks, everyone.
Yeah.